Assalamu alaikum. We have seen the example 4.5. We're actually continuing with example 4.5. 4.4 is already been solved, and we have seen that all four conditions are fulfilled for the stability, and the system is stable. So, and also if you factorize the given characteristic equation, then you're also going to see that z equal to pz equal to z minus 0.8, z plus 0.5, z minus 0.5, and z minus 0.041, something like this. So now we can clearly see that all the poles of the characteristic equation, or the roots of the characteristic equation, is within the unit circle. So all the values here are actually lesser than 1. So we can also verify that the system is stable. But the point why we prefer a method like jury's test is because of the fact that it's very difficult at times, in case, especially in case of the complex poles, to figure out their exact location. So let us continue with another example. I'll not do the complete one in this part 2. Rather, I'll try to give you a small changes or the variation in the problem that you have. So Pz equal to z cube minus 1.1 z square minus 0.1 z plus 0.2 equal to 0. So this is our characteristic equation. So this is our A0, which is 1, and A1, which is minus 1.1. A2 is equal to minus 0.1, and A3 equal to 0.2. So to proceed with this particular problem, the first condition that has been given to us is that AN, which is in this particular case is a 3 basically, the magnitude of A3, which is 0.2, needs to be lesser than A0. In our case, A0 is 1. So the condition is true, satisfied. Second condition is that PZ, or basically P1, has to be greater than 0. So we can see that if you put all the values into this equation, 1 minus 1.1 minus 0.1 plus 0.2, it gives a magnitude 0. Now we're in a dilemma, because what happens if Pz equal to P1 equal to 0? So it means is that since our condition was P1 has to be greater than 0, but we see that P1 is equal to 0. And now this is condition for stability. Okay, and this is at best we can say that critically stable. Critically stable. Okay. So what we can say is that the rest of the test we may have to conduct for not stability, rather whether it is critically stable or it is unstable. So if other conditions actually satisfies, then it represents a critically stable system. And if some of them are violated even further, then the system is unstable. So the third condition, I'm not doing it, I'm just letting it for you, minus 1. And we know that here n is odd, and once n is odd, our condition is p minus 1 has to be lesser than 0. So if you just put all the values, you're going to find minus 1.8, and that is lesser than 0. So that is also true as a condition. Now next is you have to fill up the table. So I'm letting on to you, and if you fill up the table and then find out the coefficient, in this particular case the table will be very simple, a single table. Actually I have tried with another particular table format which seems a bit reasonable to me. So let me share, and if you feel comfortable you can also use this format in the exam hall. So Z0, Z to the power 0, Z to the power 1, Z to the power 2, and Z to the power 3 in this particular case. So coefficients are 0.2 minus 0.1 minus 1.1 and then 1. So in the reverse order, 1 minus 1.1 minus 0.1, then you have 0.2. So what I preferred is that you can just directly write the determinant here, 0.2, 1.2. So this is corresponding to your B3. So you'll directly give you B3. Sorry, B2, because highest order is N. So Bn, N is here is A3. So Bn minus 1 has to be B2. So you can directly find out B2. Similarly, in the next one, first column will not change. So you can just add the others, minus 1.1, minus 0.1, and that will give you B1, magnitude of B1. And finally, the third one, 0.21 minus 0.1 minus 1.1. So you can, from here, you can find out B0. In this particular case, the magnitudes are basically minus 0.96, 1.08, and minus 0.12. So the fourth condition was that the next coefficients, highest one, that is in this particular is B2, magnitude of that one has to be greater than B's magnitude of B0, and definitely 0.96 is way greater than 0.12. 0.12. So it's also true. So as all the conditions fulfilled and except that P1 is equal to 0, so we are satisfied and we can say that the system is critically stable. Okay. Next problem, that is example 4.6. Example 4.6. What it says that in this particular case, the first condition fulfilled, condition 1, that is A3 is lesser than A0, that was true. And then the second condition where P1 should be calculated, and we have figured out in this particular case that P1 is minus 0.14, but which is lesser than 0. But our condition says the P1 has to be greater than 0, or at least P1 should be equal to 0. This is for critically stable, and this is for absolutely stable. And now, since our condition is not fulfilled here, we can say that system is unstable. So we should not proceed further with the rest of the steps. We can stop here and we can declare that the system is unstable. Now, next example, example 4.7, what it says is that example 4.7, it says that a transfer function is given, the sampling period is given, so t is given 1, transfer function g of z is given as k 0.3679 z plus 0.2642 divided by z minus 0.3679 into z minus 1. So this is given, and we are supposed to figure out the range of k. So range of k for which the system is stable. So this is a design problem, an interesting one. So first thing that you should do is to figure out the closed loop transfer function, that is Cz by Rz, and using the formula that we have learned, Gz by 1 plus Gz. So just if we apply that one, then what we are going to get is k times 0.3679z as it was plus 0.2642 divided by z square plus 0.3679k minus 1 point, so minus 1.3679 j plus 0.3679 plus 0.2642k. Okay, so we are interested about the denominator, that is our characteristic equation. So our characteristic equation Pz is essentially this one. And now, what are the conditions? And it is a second order system. So for the second order system, the conditions that should fulfill for a stable system is three conditions. Number one is our value of magnitude A2. We don't have to follow the table because of the fact that it is already only three coefficient you have. So A2 has to be lesser than, magnitude of A2 has to be lesser than A0. Then number two is P of 1 has to be greater than 0, and number three will be your P of minus 1 has to be greater than 1, because it is n equal to or even. So for even, it also has to be 1. So these are the three conditions that we have to apply on this characteristic equation. Okay, so let us try to apply. The first condition will give us for the first condition, that is uh, A2 has to be lesser than A0. So that will actually imply us the fact that 0.3679 plus 0.2642k, that is our A2 needs to be. Okay, so somehow so this one has to be lesser than 1. So if we apply this condition, then simplify a bit, then we get a condition of 2.3925. The value of the k should be greater than lesser than that, and greater than minus 5.1775. And the second condition, that is P1 should be greater than 0. So if we apply that one and plug in the magnitude of 1 and simplify a bit, then we are going to get say 0.6321k greater than 0. It gives actually eventually k greater than 0. And the third condition, P minus 1 should also be greater than 0. And that implies that P minus 1 gives us a condition something like this: 2.7358 minus 0.1037k greater than 0. So if you simplify a bit, then the value of the k should be lesser than 26.382. So this is the case. Now, if you combine these three, what you can find out, the common thing is that all three conditions should be fulfilled. So what you can see that value of the k has to be lesser than 26, and also it says 2 points. So it has to be actually follow the common one. So that is 2.3925, lesser than that. And also guys that it has to be greater than minus 5.7 and greater than 0. So basically you have to take the common one. So this is the condition or the range for which you can find out the value of the system is to be stable. Similarly, we can also find another thing, that is the frequency of oscillation. We can say that maximum value that you can apply is k equal to 2.3925. Now, if you apply this one, you are going to see that your Pz will be 0, and the system will be having critically stable. And critically stable system means you will have sustained oscillation. So if you want to find out what will be the value of the oscillation, then you can actually set k equal to this into the characteristic equation, and that will give us z square minus 0.4877j plus 1 equal to 0. So the value of the j12 can be 0.2439 plus minus 0.9698. So, and also t is given equal to 1. We know that the angle of z equal to twice by, we derived in the last class, twice by omega d by omega s. And we are interested about the omega d, the frequency of oscillation. So we can say that it will be omega s by twice pi z. So t is 1, so omega s will be twice pi by 1 is twice pi, twice pi getting cancelled out, so only the angle of z. So go there, and the angle of z will be tan inverse. We already know the coefficients, and inverse 0.9698 by 0.2439. So that is our oscillation. So if you fill it up, then you are going to find 1.3244 is radian per second is your the frequency of the sustained oscillation. Okay, so this is all about the jury method. And the other one that we have, we just give you the hints, but we are not going to use it, is the third method, stability by the bilinear transformation and the Raoult's stability criteria. So how can we do that? So for that one is basically we have to transfer our characteristic equation P z from z plane to another plane that is called W plane. So actually, this transformation is known as bilinear transformation. The z is given as w plus 1 divided by w minus 1. Likewise, omega w is also given as z plus 1 by z minus 1, where w is actually sigma plus j. This is almost similar to your S plane, but they are not exactly same. And because of that, you cannot exactly find out the pole location, and that cannot give you the stability information. So that is why now the magnitude of the z, if you want to figure out, and you just plug in w plus 1 divided by w minus 1, and that will give you, just put the value of the sigma plus j omega plus 1 divided by sigma plus j omega minus 1, and that has to be greater lesser than small, because we know that magnitude of the z has to be lesser than 1, or it has to be within the unit circle. So if we simplify a bit, sigma plus 1 whole square plus omega square divided by sigma plus sigma minus 1 whole square plus omega square. This magnitude has to be 1, or we can just get sigma plus 1 whole square plus omega square has to be less, this has to be lesser than sigma minus square plus omega square. Now, if you simplify a bit, we are eventually going to say that the sigma value has to be lesser than 0, which is similar to this one, as we already said, but they are not exactly same. And because of that, in the pole location, that's we know that we, for the pole location in the S plane, we can say that system is stable or not, but this is not true, even though it says that the poles for the stable system has to be in the left side in case of the W plane as well. Okay, so bottom idea is how to apply this one. You know already P z equal to 0, and you set z equal to W plus 1 divided by W minus 1. Then you find out another polynomial, say QZ, QW equal to 0. And once you know that, you just apply the Raoult, you form the Raoult table, and Raoult's stability criteria you apply, and you're good to go with figuring out whether your system is stable or unstable based on the number of the sign changes in the first column. But the difficulty with this one is the amount of the computation required for this method is way too much compared to the Jury's method. So that is why in most cases, this one is not used. Okay, so and that is why it is always wise to go only about the Jury's method. So you can also have omit this particular method. Okay, see you in the next lecture, that is lecture 16, inshallah, and article 4.4 will be covered. Assalamu alaikum.